Okay, so today we're going to be learning one of the simplest machine learning algorithms and one of the oldest, and it's called k-nearest neighbors. And I just always abbreviate this k. Okay. Okay. Now, if at any point in time the camera goes out of focus for too long, please speak up so I can fix that. Okay. So, what is k-nearest neighbors? So, it is a simple, very simple supervised learning algorithm. Okay. So again, supervised learning we went over last time. So the data set in question, we have the feature vectors, and then we also have the corresponding labels for each of the data points that we have. So this algorithm can be used for classification. So classification, like we did with the perceptron learning algorithm, where we tried to classify whether or not, given a feature vector, you were type this or type this. So we can use this for classification, but we can also use this for regression. And again, regression problems have labels that are continuous, that belong to some continuous set. So the labels are some real valued, the labels are real valued along the continuous set, and we're in the realm of regression. If the labels are type A, type B, some type of class in this classification. But then also K-NN has the other advantage of being able to be used as a searching algorithm. And we'll talk about that towards the end of today's lecture. Okay, so how does it work? I think the best way is to use maybe a picture, a two-dimensional picture. So suppose we have like x1, x2, and these are features, and we're supposing that the data set that we have, the features belong to two-dimensional space. So dx is going to be some subset of R2. So this is the features for our data set D. And for our labels, dy. For now, we're going to assume that we're in the classification phase for k-nearest neighbors. And we'll say that it's just, I don't know, some subset of 1, 0. Yeah, so like 1, 2, 3 or something like that. Like maybe there's like 3 labels. You're either type 1, type 2, or type 3. Okay. Now actually, no, for the picture, let's only do 2. So we're either label 1 or 2. Okay. So let's put some markers down. So maybe like this is maybe type 1 or the X's. And then the other type of data is maybe type 2. Okay. Now notice that this is not a linearly separable data set. There is no line that cuts this data into two separate pieces. But notice that if we have this data set in memory, we have access to this data set currently, and we put a new point down, then if we look to the k closest neighbors, so if we say like k could be equal to like 4 or something like that, and we look to the k closest neighbors to this box, we see there. Okay. And the way that k nearest neighbors works, it's almost like it reminds me of like a greedy approach, like a greedy algorithm approach. So we see of all of the neighbors that are with this new point, we're going to take the mode of them. There's either type 1 or type 2, right? So with this observation, we would then predict that since x's dominate everything, we would predict that this is a type x point, because the k closest feature vectors to that feature vector are of type x. So we would assume that all the type x data points kind of lie around each other, and all the type 0 or label 2 points all kind of hang out together. And that's the general idea. Okay. So in order to implement k nearest neighbors, we need some metric to determine distance. And there's many different ways to do this. For today's lecture, we're just going to use the standard Euclidean, the Euclidean distance, right? So distance is just going to be between points or feature vectors xi and xj. We're just going to say that that's going to be the square root of the sum from I is equal 1 to say L, it's an L right there, of x I, I need to use a different index here. Maybe I'll say lowercase n minus xj n all squared. So that's just the standard Euclidean distance. So how does it work? We choose a value for k, and then we put it in dimensional space, and then we calculate the distance to all the points around it, and the k closest of those for classification, the mode of that out of the k would give us our label like 1 or 2 or whatever it might be. Again, it's kind of assuming that the data, the feature vectors, all jumble together sort of in classes. Like, yes, there might be some overlap. For example, here that does have one neighbor that is a circle, but the majority of the neighbors are going to be these x's. So we would predict that that would be an x. Okay. So in classification, typically, so for classification, we're going to choose k to the odd. Because that will break the ties that might happen. You might, if you choose an even k, you might have two neighbors of class 1 and 2 neighbors of class 2. So in order to break that to classification, we typically choose k to the odd. When dealing with regression, of the k closest points to you, you take the mean of those k closest points, and that gives you your real number output. Okay, so it's a very simple algorithm. Okay, and it has advantages because it's so simple. So what are the advantages? So Simple. It's very easy to implement from scratch. I guess there's obviously going to be packages that you can import into whatever language you're looking at, but you can do this from scratch. Two, there's no optimization of parameters. And what do I mean by that? So when we looked at the perceptron learning algorithm, we were iteratively updating the weights for our model, right? We were basically optimizing our weights. Here, we're not optimizing weights at all. There's no parameters to optimize there. We're literally just doing a greedy approach, looking at the k nearest things, k nearest feature vectors to the point in question, and then the majority rules. That's the label it gets. And three, this algorithm is easy to do classification and regression. There's no major changes that you need to do in order to switch from classification to regression. And it has this added benefit of search, or maybe recommendations that we can also apply it to. So what are the disadvantages? I was going to write a little bit more, but I'll just write this. It's slow. So imagine that you have like hundreds of thousands of data points, right? You have to keep all those data points in memory in order to calculate the k nearest points to the new point that you put in dimensional space. So it can be computationally difficult to do that, or not difficult, but slow. If you have to calculate the distance between this point and every single other point, that just imagine doing that 1,000,000 times, or even higher, right? That's the main disadvantage of KNN. And I suppose second, I'll say that it is maybe sensitive to high dimension feature vectors. So when your feature vectors are very high dimensional, this notion of distance might not capture really how the points are relating to each other. And at least from my own experiences, I've seen that when you have these high dimensional feature vectors, typically what you can do is combine principal component analysis together with k nearest neighbors to then make predictions. And I don't know if you saw PCA, or principal component analysis, in advanced linear algebra. You should have. I know when I teach that. But principal component analysis is basically a way of reducing the dimensions needed to extract the features that are important. So if you have a bunch of features that don't really matter, you want to get rid of those and look at only the features that do. And when you do that, you can reduce the dimension of your feature vectors, and then k nearest neighbors can be something that you apply to that after you reduce the dimension. Okay, and now that I've mentioned advantages and disadvantages, I'll say that it's been my most used algorithm in practice. So I do a little bit of consulting as a data scientist for this company. And for example, the first project that I worked on which is now an app on the App Store, like, and the K-nearest neighbors are using it. So this app, it takes, so you have like, people need credit approval, right? And they have several features that they have to fill in, like, on the app, right? And then they want to get matched with lenders that are willing to lend them money for whatever purpose, and the purposes can like vary. So you have like a bunch of yes, no, you have how much you want to borrow, these types of things. And that's a feature vector. And you want to pair those feature vectors with the lender that has the closest criteria. So you think of like lender 1, lender 2, and that's a person you put in there. Which of the lenders are they closest to in Euclidean space, according to the feature vectors, which are numerical. And it works. It's, like I said, it's not the fastest, but it works. And the app is functioning and people use it. And it was incredibly easy for me to do. It took me like an hour or something like that. Okay. So any questions about the general idea behind K-nearest neighbors?
I have a question about how do you choose your K?
So I was going to get to that when we were programming, but we can go ahead and talk about that now. So you can imagine if you chose K to be 1, you might have a lot of errors, right? Like, for example, if K was 1 and you put like your, suppose there's like a blue vector there or something like that, or maybe it's like here, and it's like closer to that one, right? Then that would make a bad prediction, right? But what if you chose K to be 10 or maybe 6 or something like that? So then you get paired there, and then there, something. So the way that you choose your K, there's several different ways to do it, but I think for our purposes, the best way to choose the K is to measure the error that you incur for different values of K. So test K is equal to 2, K is equal to 3, K is equal to 4, K is equal to 5. Each of these is going to incur some error, and there's going to be an optimal K that you can choose for the data set that you're given. So that's how you would choose your K for our purposes. Any other questions? Have any of you programmed K-nearest neighbors from scratch before? You can just say yes if you have. No? Okay. So I'm going to go ahead and pause the video. Okay. So let's go ahead and get started. So to implement K-nearest neighbors, we're going to use the iris data set to get started. So I'm going to say I'm going to use our data sets. I'm going to use plots, so using plots. And then we're going to read in this the CSV file in a bit. So I'm going to say using a CSV to read that in. Okay, so that's the first thing I'm going to do. So I'm just going to run that. Okay. So while that's running, I'm going to go ahead and get my data. So iris is going to be equal to data sets or data set, sorry. And we're accessing data sets, and we're accessing the iris data set. Okay. So by the way, this might be a little bit fun. It might be a little annoying, and I apologize, but I haven't done this in a while, so probably since last semester. So I might be a little bit rusty putting it together, but we'll make it through, and you'll see how like I problem solve if I have any mistakes. So that's still loading there. So let me just go ahead and get my X data. So I'm going to use 3 features this time instead of 2 features. So I'm going to say X for X in zip. And I'm going to look at sepal length. And then iris, maybe sepal width. And then maybe iris petal length. So I'm going to have triples of features. That's what this is doing. So I'm zipping those into these triples, which are tuples inside of this array. It'll make it nice to plot in a bit, that data. And then I can say y data is going to be equal to iris dot species, so access to species data. This is probably unnecessary, but just to be safe, iris species I, or I equals 1 to 150. Again, just some simple list comprehension here. So then, okay. So that's just me reading in that data. Again, the first time you run packages in Julia, it's going to be a little bit slow. So let that run. Okay, so just to like verify real fast, iris or X data 1. Triple, and then Y data 1 label. Okay, so let's go ahead and plot this data to see what it looks like. Just it's always nice to have some visualizations as you're going along. So I'm going to scatter the data. These are all points, and I'm going to set up my plot first by giving all the axis labels in the title. So I'm going to say X axis equals to sepal length. That's the first entry of those tuples. Y-axis equals to sepal width. And then Z-axis equals to petal length. And then I'm going to give it a nice little title. Iris 3D plot or something like that. So then once I've made this template for a plot, then I'm going to start putting on my data. So now I'm going to modify that plot with the exclamation mark there. And I'm going to plot X data 1 through 50. I know those come from the first species. Okay, and that species is the Setosa. So I'm going to give it the label Setosa. Okay. And then after I do that, I'm going to do the next 50. So scatter exclamation mark to modify that plot. X data 51 through 100. And I'll give that the label Versi color. And then finally the last 50. So X data 101 to 150. And then label equals Virginica. Yeah, Virginica. Okay, so let's go ahead and look what that looks like. All right, so we have a nice little 3-dimensional plot here of all our features, our feature vectors. And since I plotted them separately, we can distinguish between Virginica, versicolor, and Setosa. Okay, so next, in order to implement k nearest neighbors, we need a distance function. And again, we're just going to use the standard Euclidean distance. So in Julia, I'm gonna write a function to do that. Maybe distance. And this is the Euclidean distance. There could be others, but we'll just see. And this is going to calculate the distance between maybe 0.1 and 0.2. Okay. And we're going to return the square root of the sum of P1I. I need to put this in parentheses, P1I minus P2I all squared. Okay, I'm still in the sum. For I equals 1 to the length of P1. And we're taking the square root of that in that function. So I need to test to make sure this function works before I go any further. So distance between x data 1 and x data 2. Let's make sure that works. All right, so we have some distance. Let's look at the distance between that and maybe 112. So you can already see that the distance from label 1 to the vertices, or not the vertices, the feature vectors after 100, the distance is 4. But if I put it with something in the same class, it's small. That's the general idea, is that everything in this cluster belongs to the same label. Everything in this cluster roughly belongs to the same label. You see there's a little bit more mix up here than there are between Setosa and the rest of them. But versicolor and Virginica, there's some overlap. So that's going to be where we're going to have to test and be careful.
Well, I had a quick question. What how is your data stored? Like, what format is it stored in?
So I read in the Iris data set is a data frame, but then I make my feature vector, my feature set in my label set as tuples. So tuples here, and then my labels are just strings.
Okay.
So for example, if I look at x data 1, so that corresponds to 5.1, 3.5, and 1.4, which are the features for the first flower in the data set, which are measurements of the sepal length, sepal width, and petal length.
Okay.
All right. So I typically do when I'm programming on the fly. I write a function and I immediately test it before I try to use it anywhere. Okay. So now we can write a function for the k nearest neighbors. So function, I'm going to call it k and n. And this is going to take in a point P and some features, labels, and a k that we don't know what that is yet. We're just going to pick one at random and see how it works at first. Okay, so what do I want to do now? I need to calculate the distance from my point P to every other point, all these other points. And by the way, I don't have a train and test set right now. I'm just doing it on the whole thing, and then I'm going to go back and make like a train set to make my k later. Right now, I'm just trying to get it to work on the full data set. And then I can go back and fix it afterwards. So I need to calculate the distance from here to all the features. So I can say, maybe I'll just sort all those or put them in an array somehow. So maybe I can say distance array equals P X. No, I need to have an index here. So P features I. Okay, and then maybe do distance between P and features I, and then do the labels I, for I equals 1 to the length of features. Does everyone understand what I just did? So maybe I don't need to store P. I just have the point in question, the distance from P to that point, and the label of that point, all stored in a triple. And this is for each I in 1 to length of feature. So it's like, I'm just calculating the distance from P to each of the points in the feature set, and I'm saving the distance, the point, and the label. In fact, I probably don't even need to save the point. I could just save the distance and the label. Yeah, I'll do that instead and see if that works out. So now this is kind of simple. I store distance and then the label. Okay. So then once I do that, each entry in here is going to be, so let me just like show you what I mean. I don't want to leave anyone out. So I'm going to copy that, come over here and paste it right there, and replace P by X data 1, and then I'll call this X data. I'll call this Y data. And then I know I don't want to look at 1, so I'm just going to say like, this is like 2, and I'll call this X data. And I'll label this thing by maybe test array or something like that. So I just want to illustrate what exactly this is doing. Put a cell underneath there. That. So look what it made. It has a distance and a label. Distance label, distance label, distance label, distance label, right? And this array is storing the distance from X data 1 to every other point in my feature vector, my feature space, or training data, I guess. And so the first entry is the distance, the second entry of the tuple is the label. So once I have this information, then I can find the closest ones. So if I wanted to look at maybe like 120, and then I'll just start at 1, it doesn't matter, I'm just sort of going through the training data. I see these distances and I see the labels. So all I need to do now is to sort this array in terms of increasing distance, right? So if I make my test array like that, then I could do sort, and I'm going to sort test array by, this is, for those of you programming in Python, this is almost like using a lambda function to sort a list of tuples based off of certain entries. So I'm going to sort this array by with the function x goes to x1. So I'm sorting this list of this array of tuples by the first entry of each of the in that array. So see now, once I've sorted, I see the distances are in increasing order. And then if K was like, I don't know, 3, those are the 3 closest flowers, so the majority would be Virginica. So I would say that that was a Virginica. So now I just need to put that into a function that I can call whenever. So just like I did up here, I guess I'll just copy this. The easiest thing to do. So I'm going to sort that, and then I'm going to return the top k things. So return distance array from 1 to k, and then in that function out. Okay. So let's look what this does. So like k and n, say x data 40 or something, I don't know, and then x data, and then y data, and maybe k. Now we got to pick a k, so let's just say 4. So those are the 4 closest feature vectors to the given point. Okay. So you see how that works now. So now we can make a predictor. We can just say, we can say function, say maybe knn predictor, point p, features, labels, and then k, and then neighbors equals to knn of that stuff. So then we just need to take the majority instances. So I guess I can do this kind of like in an ad hoc manner and say something like, maybe something like, how can I do this? What's the cleanest way to do this? I guess I could just put all the labels in the array and then just count them. So I can say like neighbor labels equals to x2 or x and neighbors. And the labels, so how can I do this? I just want to count them, and I don't want to do it in an ugly way. Go back up here and say, I guess I'll make this, just to make life easier, I'll make this specific to iris data set. So I can say something like, I can say Setosa count is equal to 1.0 for x in neighbors if x2 equals Setosa. And then Versailles color count equals to 1.0 for x neighbors if x2 equals Versailles color. And then finally, Virginica count 1.0 for X and neighbors if X2 is equal to Virginica. So once I have those counts, then I can just pick the majority. So, so which one has the biggest? So I can just assume that Setosa is the biggest and then go through and change like just a normal max algorithm. So I'll call it like M equals to sum of, no, I'll say like maybe majority equals to Setosa maybe. And then for, I'll just do two quick if statements. If sum of Setosa count is less than sum of Versailles color count, majority equals Versailles color. Okay. And so, okay. So maybe elif so if that doesn't happen, let's see. I don't want to do this ugly. I hate writing ugly code. So I'm thinking right now the best way just to get the mode without calling in any extra functions. Let me think about this. Oh, I'm dumb. I can do this in like one line. Okay. So, 10th list or something is equal to Setosa, comma, Setosa count, comma. I'm making these tuples now. Versailles color, comma, Versailles color count, comma, Virginica, comma, Virginica count. And then I'm just gonna cheat. There it goes. I'm gonna sort this thing. Sort temp list by equals X goes to X2. So I'm just sorting this by the second entry now. And then I can just return temp list end, which is after you sort it, it's going to be at the very end. And that last entry, I just want the label that corresponds to it. That's an ad hoc way of doing it. So let's see if this works. What we have, so K and then Iris, the Victor. So let's look at like X data, maybe 120, and say X data, Y data, and we'll take K to be like 5. So that let me just,
I have a question.
yeah.
Up in your K&N function, when you do the sort, you have test array. Should it
Oh, that's
be
bad.
distance array?
Yeah, it should be distance array. That was going to mess something up. And I bet you that's why this was off. There it goes. Thank you for getting that. That copy and paste I did earlier would have gotten me in trouble. But look, we predicted it's Virginica. And if we wanted to, yeah, so we predict this is a Virginica. Okay, so this is just the bare bones, just getting it working. And then now that I have it working, what I would do normally if I was working on my own is I would go back and I would look at the first 40 species from each of the 40 instances from each of the species. That would be my train data. And then I would test it on the species that I didn't see. And that's how I would pick my value for K. Whichever K gave me the least error, that would be the one I would pick. And this is, you should use classification error on this in order to measure your error. Okay. So I am going to pause the recording again. Okay. So I'm going to pause it. Share screen. Okay, just so the recording has this. So we're going to write a predictor function that takes in a movie name and then recommends to the user whether or not they might want to watch it based off of how similar it is to other movies. So the movie's recommendation data that I provided on Blackboard, it's a CSV file, and we read that in as a data frame. And then the data frame has these columns, which we have movie names, and then we have the IMDb rating, such as it's a numerical value associated with the name. And then we have, is it a biography? Is it a drama? Is it a thriller? And there's 5 other columns that aren't listed. But again, we just have features and numerical values associated with those features. So if we pick a movie that we haven't seen before, like A Time to Kill, we can look at the K nearest neighbors in dimensional space to this movie. And if these movies are movies that we've seen before and we like, we were likely to click on this Time to Kill. So for our features, we're just going to use these 4. We could use more, but let's just use these 4 and see what happens. So the rating, biography, drama, thriller. So we have our X movie data as these tuples consisting those values, and then we have the names. So then if we just look at the X movie data, we have these tuples that correspond to the feature vectors of each of these movies. So let's go ahead and write a function that's going to provide movies that are similar to the movie that we have in question. We're going to provide a movie name, and then we're going to provide features, and then we're going to provide labels, and then we're going to provide a value K. Okay. So what we can do is, well, we can say something like, what was the name of the function I had up here? It was just K&N, right? K&N took a point, features, labels, K. Okay, so I'm just going to say neighbors is equal to K&N. So I need the corresponding point that goes with that movie name. So how can I do this? I can say, I need to play around with this for a second. Movie data and say, what does that do? What did I call it? Movies. annotation game. So that's the, oh, I can do, I don't have to, I know what to do. So I'm gonna say for I equals 1 to the length of labels, I'm just gonna find that movie. If I'm gonna say labels I equals movie name, now I can just call my KNN function. Neighbors equals KNN of features I. So that's gonna grab my feature vector, feature tuple, and then I'm gonna have labels, and then, oh no, I need to provide features, labels, and then K. So this will calculate the K nearest neighbors to that feature vector, which corresponds to that movie. So then we can just print out, so we like print line. So we can say the top K similar movies with the movie name that you provide are, and then we just need to print out the neighbors, right? For say J equals 1 to the length, oh, it's just K, print line, and I'm gonna say J period, and then maybe neighbors J, and how did that return? So it's the second entry is the label. So I'm going to say neighbors J2 in that for loop, and then end, and end, and end. Okay, so let's see what this does. I'm just going to pick a random movie name here, and then I'm going to say more like this. That's the name, and then I'm going to say X movie data, Y movie data, and I'll just pick, I want to know like the top like 7 similar movies. There you go. And it's kind of nice. I can just say maybe pick Terminator. I'm curious to see what it says. So if I put Terminator in there, oh. I don't like that it includes the Terminator here. So I can fix that because I know the closest movie to the Terminator is a Terminator. And I know that my neighbors are already sorted. So I can just start my indexing at 2 here. And then here I can just put a K plus 1. And here put a K plus 1. And now maybe I can do that. Is that going to give me an error? There it goes. So now these are the top 7 movies that are similar with the Terminator. And it looks more or less kind of there, maybe. Maybe what I can do now is I could maybe add some more columns and see how well it performs then. Okay.
So this is how k-nearest neighbors can be used as a recommender system. Okay. All right, so let me go ahead and stop the share there now. Any questions? Let me go ahead and stop the recording now.